So, in the last video, we talked about cold gas thrusters and monoprop engines. We saw that monoprop engines were not efficient and didn't produce any thrust as they were not using the chemical properties of the fuel. So, we want to pump the propellant into the engine. Obviously, a pump increases the pressure a lot, and as we know, pressure is a good thing. But running a pump requires energy, a lot of energy. So perhaps the easiest way to power a rocket pump is with electricity. That's right. That is now a reality in spaceflight. You can run a rocket engine with pressure from a pump run by an electric motor, powered by a lithium ion battery. And so now we are adding a little bit of complexity, but our biggest advantage is now the pressure inside the tanks. We can go from something like 30 bars down to only 3 bars of pressure. And as you can imagine, that makes the tanks much more lighter. So as long as the weight is saved on the tanks, the weight of the pumps, motor and the batteries can be compromised. Batteries are less power dense than a turbine and propellant. Because of these limitations, electric pump-fed rockets were actually considered impossible until recently, as battery technology has finally good enough to even make this a viable solution for an orbital launcher. But just barely, Rocket Lab has pushed through that barrier and was successful in making the first electric pump-fed orbital rocket in history, the Electron. Since they have paved the way, Astra has followed in their footsteps with the Dolphin engine on the first stage of their rocket, as well as had become a popular choice for a new rocket companies because of its relative ease of development and higher performance than a pressure-fed system. And due to the less scalability of the batteries, it is not a viable solution for larger rockets. So, what if you need more performance? Well, I think it's time we dive down into the energy of fuel to spin the pumps and run our rocket engine. So, as we have mentioned, it can take a lot of energy to spin a big pump fast enough to flow ridiculous amounts of propellant into the combustion chamber at very high pressures. Although 230,000 horsepower is at the upper end of the power requirements, tens of thousands of horsepower are still in the realm of most orbital rocket engines. So if instead of having an electric motor spin the pumps, let's just basically take a small rocket engine and point it at the turbine and allow that high velocity, high pressure hot exhaust gas to perform mechanical work. Well, that's the idea behind the open cycle, otherwise known as the gas generator cycle rocket engine. You basically create a small rocket engine whose sole purpose is to generate high pressure hot gas that can be used to spin the pumps that feed the engine. One of the earliest examples of this was the German designed V2 rocket with the A4 engine. Instead of using the main propellant, chose high concentration hydrogen peroxide as fuel and then ran it over a potassium permanganate catalyst that can create enough energy to spin the turbine up to the right speeds. So the pressure inside the gas generator can be really high, whatever it takes to get the turbine up to the right speed to power the pumps. But of course, this brings up to a conundrum. If the pumps are powered from the gas generator and the gas generator is powered by the pumps and the pumps need the gas generator to run itself and the gas generator needs the pumps to run itself. You get the point. Well, starting a rocket engine is a whole different topic altogether, so we will save that topic for another video. But the most common thing to do is just basically shoot a separate cold gas thruster at the turbine to get it spinning. Before the engine actually starts to run, this is called the helium spin start. With the gas generator, all the exhaust gases that were used to spin the turbine are simply dumped overboard, or perhaps will be used to cool some portions of the nozzle, but the gases are not added into the main combustion chamber. That's why this is called open cycle. The exhaust gases is used and then it is expelled to the open air or space. It is not used in any part of the main combustion process. The downside with the open cycle is that there is a ton of unburnt fuel in the exhaust. See how sooty the exhaust gases from the gas generator can be. That's just unburnt fuel being wasted and thrown. So the open cycle always wastes some of the propellant in order to power the pumps, but generally it's considered worth it because it is relatively small amount of fuel compared to the amount of fuel used inside the combustion chamber. Some good examples of gas generator open cycle engines are the Merlin 1D engines on SpaceX's Falcon 9, the F1 engine on the Saturn V, the RS-107A and the RS-108A, the Soyuz and the RS-68 engines on the Delta IV Heavy, and many others. It is easily one of the most common cycle types of orbital rockets, being extremely effective, high capable and relatively easy to develop compared to the other counterparts. It is the most common choice of many rocket companies. But what if you are still not hitting your target performance and you are crying at the thought of wasting fuel and dumping it overboard? Well, what if we could pump that exhaust gases right into the engine and not waste any fuel? Well, that will be the topic for the next video, so stick around till then, and if you like what I am doing here, you can subscribe to the channel. That will be it for the video. Thank you. Goodbye.